You ever stop and just wonder about the invisible science that makes everything tick? Well, today we're going to pull back the curtain. We're taking a wild journey from the super weird world of quantum physics right into the gadgets you're probably holding in your hand. So let's dive in.
Okay, so what do traffic lights, medical sonograms, and your credit card all have in common? I know, it sounds like the start of a really bad joke, right? These things seem totally random. But what if I told you there's a hidden connection, that they're all powered by the exact same set of, frankly, bizarre scientific rules?
Yep, the secret ingredient here is quantum mechanics. In this explainer, we're going to see how the truly mind-bending, almost magical behavior of the universe's tiniest particles is the bedrock for the technology that, let's be honest, runs our entire world.
All right, first things first. To even begin to understand this, we need to meet the star of our show, the one and only, the electron. Seriously, getting a grip on its weird little habits is the key to unlocking, well, pretty much all modern technology.
So when you think of an electron, you probably picture a tiny little ball, right? Zipping around the nucleus of an atom like a mini planet orbiting a sun. That's what we all learned. But quantum mechanics kind of threw that idea out the window. It tells us it's way stranger. An atomic orbital isn't a neat little track. It's more like a fuzzy cloud of probability. It's just a region where the electron is most likely to be found.
Okay, a probability cloud sounds abstract. So how do we even picture that? Well, think about a drum. When you hit a drum skin, it doesn't just move up and down, right? It vibrates in all these cool, complex patterns. Electron orbitals are kind of like that. They're the different vibration patterns or shapes where an electron is allowed to exist, each with its own specific energy level.
All right, so if you thought probability clouds were weird, you might want to buckle up, because now we're going to look at one of the electron's other superpowers. And this one just flat out seems to break the rules of reality.
It's called quantum tunneling, and it's wild. Look, in our world, if you throw a ball at a solid wall, what happens? It bounces off. Duh, it doesn't have enough energy to go through. But down in the quantum realm, an electron can just pop up on the other side of a barrier. It can literally appear on the other side without ever having enough energy to actually go over it.
And here's the crazy part. It doesn't break through the wall. It just, well, it appears. It's just there. Like the wall didn't even exist for a second. This sounds like something out of a comic book, but it's not. It's a real, fundamental feature of our universe. And believe it or not, our tech depends on it.
Okay, so we've got these electrons with their probability clouds and their wall-phasing superpowers. That's neat. But how in the world do we get from that weirdness to a working smartphone? Well, the whole game is about one thing: learning how to control the flow of those electrons. You know, what we call electricity. Let's quickly break down the basics. In some materials, like a copper wire, a conductor, the electrons are basically free agents. They form this big electron sea and can just cruise around wherever they want. That's why electricity flows so well. But then you have insulators, like glass. There, the electrons are locked down tight to their atoms. They're not going anywhere.
But here's where the real magic comes in. There's a third category: semiconductors. They're kind of the Goldilocks of materials. Not a great conductor, not a great insulator, just somewhere in the middle. And that's their superpower. Because we can tweak them, we can fiddle with their properties to turn them into perfect little on-off switches. This ability to precisely control the flow of electrons, well, that's the foundation of literally everything electronic. So we've figured out how to control electrons. Great. Now what can we do with that? Well, one of the first and maybe most brilliant things we figured out was how to make those electrons create light on command. And that brings us to the humble but world-changing LED.
This right here, this is the quantum leap in action. It's beautiful. Inside an LED, what we're basically doing is giving an electron a jolt of energy, pushing it up to a higher energy level. Think of it like pushing it up a ladder. But it can't stay up there forever. Eventually, it falls back down to where it wants to be, its lower energy state. And when it falls, it releases that extra energy as a single, tiny particle of light, a photon.
So let's walk through it step by step. First, we apply some voltage. This shoves the electrons towards what we call holes. You can just think of them as empty parking spots, just waiting for an electron. When an electron sees one of these spots, it falls right in. And that fall to a lower energy state is what releases the photon. Now do that billions upon billions of times every single second, and what do you get? Bright, beautiful, incredibly efficient light. And the progress we've made? It's just
staggering. I mean, look at this. You can see the absolutely exponential explosion in how bright these things got. What started out as a tiny, dim little indicator light you could barely see became a blindingly bright powerhouse in just a few decades. This wasn't just a little step forward. It was a complete revolution, and it was all thanks to getting better and better at controlling those little quantum leaps.
And of course, you see the results of this revolution literally everywhere you look. The traffic lights that never seem to burn out? LEDs. The super bright, instant-on taillights on new cars? Yep, LEDs. Every single one is a tiny testament to our ability to boss electrons around inside a tiny little chip.
Okay, so controlling electrons in semiconductors gave us light and computer chips. Pretty good. But what happens when we start applying these same kinds of ideas to other materials? Well, it turns out you can unlock a whole new set of what you could honestly call material superpowers.
Let's talk about piezoelectricity. This is one of my favorites. It's a fantastic two-way street. You take certain crystals and you squeeze them, and they create electricity, a voltage. Then you do the reverse. You apply electricity to them, and they physically change shape. Squeeze for power, power for movement. It's this perfect direct link between physical stress and electricity.
And this one single property is the secret sauce behind a ton of amazing gadgets. Remember that medical sonogram from the beginning? That's it. The little wand uses electricity to change shape, sending out a sound wave. Then, when the echo comes back and squeezes it, it creates an electric signal that makes the image. But it's also in something super simple, like the push-button starter on your barbecue grill. That click? That's you squeezing a crystal to make a spark.
And it's not just squeezing crystals. We have totally leveled up our magnet game too. By mixing in rare earth elements like neodymium, we can now make magnets that are ridiculously powerful for their size. I mean, incredibly strong. And that huge leap in magnetic power is exactly what makes things like tiny, powerful electric motors and modern hard drives possible.
And believe it or not, things get even weirder when you start shrinking materials down to the nanoscale. I mean, really, really tiny. The rules just change. The properties you thought you knew just go out the window. For example, a big chunk of gold is, well, it's gold, right? But if you take that same gold and chop it down into teeny tiny nanoparticles, it can actually look deep red. At that tiny scale, quantum effects just take over and completely rewrite the book on how things look and behave.
Okay, wow. So we've seen quantum leaps making light, we've seen semiconductors working as tiny switches, and we've seen materials with some serious superpowers. Let's tie this all together. Let's bring it all home by looking at one single object that you've probably got in your wallet or pocket right this second. Yep, your humble credit card. It is a perfect little museum of applied physics. That magnetic stripe on the back? That's a whole bunch of tiny magnetic particles storing your data. That little smart chip? That's a full-on mini-computer built on all those semiconductor principles we just talked about. Even that shiny little hologram is an incredible piece of material science designed to bend light in very specific, complex ways. It's amazing! It's a pocket-sized monument to how we've managed to tame all these fundamental forces of nature. So there you have it, from the quantum leap right to your fingertips. We've just seen how 100 years of digging into the weirdest, most fundamental rules of the universe has built the world we live in today. And it really makes you think, doesn't it? What are the strange, mysterious scientific principles being discovered in labs right now that will end up being the everyday taken-for-granted technology for our kids and grandkids? What's coming next?